Welcome back, friends. Today we are going to solve LeetCode problem 63, unique paths 2. Here a robot is given in the starting position, and robot wants to reach to this ending position given by star, right? And there can be obstacles, like this is representing in red color, so this is an obstacle, so a robot cannot go through this cell. So let's just quickly read this description. A robot is located at the top left corner of m by n grid marked start in the diagram below. The robot can only move either down or right at any point in time. The robot is trying to reach the bottom right corner of the grid marked in the finish. Now consider, if some obstacles are added to the grids, how many unique paths would there be? An obstacle is a space marked as 1. So as you can see, this is the obstacle, and if you look at the obstacle grid, which is the matrix that is given to us, you can see 0 0 0 here. So this is 0 0 0, then this is 0 1 0, so this is 0 1 0. So they have marked 1 for obstacle here, and the last one is 0 0 0, right? So 0 0 0 means 0 means it is available for the robot to move. So robot can move in like this, or it can move like this basically, because 0 is available, but robot can go like this and this, right? Because it is obstacle. Or robot cannot go like from here, it cannot go like this because this is obstacle in the middle, right? So that is what the problem says. So we are, let's just take this example over here. So I am taking like two examples to explain you what are the steps, how we are going to build the solution. So we are going to use dynamic programming approach to gradually formulate a solution. So the we will know how many paths a robot has, actually unique paths to reach from the start to the end, right? So so as you can see, the robot is standing here. So here is our robot start standing. This is the starting and this is the ending point, right, where robot want to reach. So we will be, first we will do m by n empty m by n dp array, right? This is empty in the beginning, which is just like 0, basically empty, right? So we will populate that dp array gradually. So how we are going to populate this dp array, so I will explain you. So we know that robot can only go on the right side or on the downside, right, downwards. So these are the only two directions which are possible for robot to move. So if robot is standing here in the first row, there is only one way to reach to this cell, right, where it is standing, because it cannot go from anywhere. Like it is already, you can just put one here because there is only one way to reach here. So if robot want to go to this cell, right, then there is only one way robot can go, by just going on to right side. So we will just write one here, right, in the dp array. And if robot want to reach this cell, then it will again walk on the right side, right, like this. And there is only one way to reach there because of that, right? Because we only have two ways of directions, either it can go right or it can go downwards, right? So we are done, we have filled the first row. Now we will look into first column, right? So now robot can go downward to reach to this cell. So it is only, there is only one way to reach to this cell. And if robot is standing here and it want to reach to this cell, it can only go downwards, right, to reach to this cell. So there is again only one way to reach there, right? It can just go downwards. So now we have filled uh, like the first row and the first column, we have filled all the ones, right, because there is only one way to reach to those cells. Now let me change the color. So now this is the obstacle which is given to us, right? So obstacle means we will be having only zero way to go there, right? You cannot go because it's obstacle. Now what we are going to do is, how many ways we can reach to any of these remaining cells, is you have to find the diagonally connected cells. Like these are the two diagonally connected cells for this cell, right? This is the cell that we are looking at, and these two are diagonally connected cells. So you have to add these cells. So 1 plus 0 you will add and you get 1 here, right? So similarly, if you are looking at this cell, right, this cell you are looking, so you have to add these diagonally connected cells. So these two are diagonally connected cells for this cell. So this is 0 plus 1 is 1 you will add here. And for this cell, last cell, you will add these two cells, right? These are two diagonally connected cells for the last cell. So this 1 plus 1 you will add 2 here. So this is the minimum ways that like unique paths basically that the robot can take to reach to the final destination. So you have to return 2 here, right? So that's why when you look at the answer you will get 2 here, right? And you can also look in this, I will just highlight the path for you. So the only two ways robot can take to reach is this one, right? This is one way, and robot can take other way as this is another way. So there are only two possible ways to reach to the ending cell, right? So now we have already seen one example. So now let's say instead of here uh, the like obstacle is on this cell, right? Obstacle is placed here. So as in the beginning we will just populate this 1 1 1, right? This 1 1 1. First row we will populate with 1 1 1, and first column we will again populate with 1 1 1, right? Because there is only one way to reach here. Now when we are reaching like this cell, we will calculate this 1 plus 1, so we get this 2. Then we will calculate here we will get 0, right? Because this is obstacle, so we will have to put 0. We cannot reach to this cell. Now to reach to this cell we have to consider the two diagonally connected cells. 2 plus 1 is equal to 3, so we have 3 here. And then we have to take these two diagonally connected cells, right? These two cells we have to consider to calculate this. So 0 plus 3 is equal to 3. So in this case you will return 3 as the unique paths that robot can take to reach from source to destination. And I will just quickly show you what those paths are. So robot can start from here, it can go here, then it can go here. This is one path, right? Then this one is the another path will be just robot will go downward like this, and it will go on the right side. So this is another path too. And the third path will be robot will start like this. From here it will go here, and from here it will again come downwards and then again go right. So these are the three unique paths that we have to return as the answer, right? So this is how we gradually build the dynamic array here, DP array, and then the last cell value we have to return as our answer, right? So one other thing I want to also mention is if for example if this obstacle, right, if obstacle is in this cell, right? Let's say obstacle is in this cell where which I am highlighting here. If the obstacle is here, then in that case our DP array will, what we will do is when we are filling our first row, right? So let's just draw the matrix quickly. So here one as we will put, but now this one is the obstacle, let's say, then we have to put 0. So once we have any obstacle in any of the cells, then it means that you can never reach any of the further cells, right? You will always have to put 0 here because you cannot go from that through that cell basically. And same thing applies to the column also. If you have obstacle, let's say in this cell you have obstacle, then if you put, you have to put 0 here. But once you put 0 here, then you cannot go through this cell, right? So you will always have to put all the zeros here for all the columns, for all the rows here basically, right? So that is one thing. So let's just look quickly into the how the implementation works here. So as you can see, first I just have this total paths function, and I am passing the obstacle grid that is given to us, and I'm calling it as a matrix here. I am getting the m as a row and n as a columns, and I'm creating a DP array here, right? With the same DP arrays has the same length and width as the obstacle grid, right? Same m by n, right? And now what we will do is, first we will create a variable called as obstacle in way, right? And we will start, like, first we want to populate this first row, right? So we will always check if matrix of ij is equal to 0. Matrix of ij means we are checking the cells in the first row basically, and there should not be any obstacle in the way, right? Because if obstacle is in the way, then we cannot go there basically. So if there is no obstacle in the way, we will just populate dpi0 is equal to 1. For example, this is 1, then this is 1, then this is 1, like that, right? For that first row. And if there is some obstacle in the way, or if the matrix ij is not equal to 0, right, then we will have to populate I0 is equal to 0, right? So in case of obstacle, we will populate I0 is 0 here on the first row, and we will just put this obstacle in a way is equal to true. So always, for the remaining cells in the first, you mean the remaining columns for the first row, we will have to put a 0. Once we have any obstacle, any cell we find in the first row, the remaining columns will always be 0 for the first row, because we cannot go through the obstacle. So same logic we have applied in when we are doing, like, if robot is going downwards, right? So in the first column it is moving. So that's what we will just say, obstacle in a way is false in the beginning, and we will check if 0 comma j is equal to 0 and there is no obstacle, we will populate that as a 1, right? So 1 1 1, like that. But if there is any obstacle in the way, we will just say dp of 0 comma j is 0 and obstacle in way is equal to true. So for example, if obstacle is here, right, let's say this cell is obstacle, then we will put a 0 here, but now we have to go put 0 everywhere else, like 0 0 0, like this, for all the remaining rows for that first column basically. So that's what we are doing here, right? So I explained you already, I think, in details. So now at this time we already have filled our first row and first column. So first row and first column we have already filled in this code. So now we are going to handle the remaining cells, right? So remaining cells means, if the matrix means if it's equal to 0, right, means there is a space for movement, we are just going to add the diagonally connected cells here in dp of ij, basically is equal to dp of I minus 1j and dp of ij minus 1, means these are two diagonally connected cells basically. So for example, if you are looking at these three, you are adding these two cells, these are two diagonally connected cells for this cell, right? So like this, that's how you will populate the dp array, and at the end you are going to just return the last cell. And let's just, so this is the code, this is our first example that we discussed, and second example, right? This first and second that we discussed here, I took it here, and this is another example. So let's just run the code and make sure it is working fine. So as you can see, first is 2 and second is 3, right? So in our example also, first is 2 and second is 3. So it is giving us correct answer, and for third it is 1. So let's just quickly submit this code. So the code is working and getting accepted. So so this is the way you can solve unique paths for robot, and you can use the dynamic programming approach. You can gradually populate the dp array, and you have to just return the last cell of the dp array. So I often create videos related to LeetCode problem solutions with Java J2E technologies, and helpful interview related videos for Java J2E technology and coding solutions. So please subscribe to the channel, it helps the channel to grow and reach to more people. Thanks for watching the video.